Hello everyone. My name is Cindy. I'm a neuro and I'm going to take you through our EDA code. So we're going to start with the libraries. Uh, Import OS. This one is for file paths and directories. Then pandas. It helps to handle tabular data, like data frames. Then we have NumPy. This works with numerical data efficiency. Then we have matplotlib.pyplot. This one is for data visualization. Then we have MNE, and this one is going to help us with our data set. It's going to help with EEG data processing. Then we have scipy.signal. This one is going to help provide signal processing functions like filters. Then we also have scipy.stats. This one is it's going to help us to compute statistical features like skewness, kurtosis. Then, so this folder path, it helps, this next line 11, it's going to help us to define the folder path and load the EEG files. Like this gives us the directory where the folder is, and the script checks if the folders exist, and if not, it throws an error. You can see if not os.path exists, folder path, erase a file not found error. Yeah, but if it exists, it lists all the .edf files in that folder. You can see file list F for F in OS list directory. Yeah, so the third step is to define the bandpass filter, and this Butterworth filter, it helps to remove noise by allocating only frequencies between low cut and high cut. So when we look at it, it's here. So when we look at it closely, you can see the demarcations. So now we have the frequency band path definitions in hertz. So the delta represents deep sleep, that range of 0.5 to 4. It represents deep sleep. Then the theta, this range 4, 8, it represents drowsiness and deep relaxation. Then the alpha, this range represents a state whereby someone is relaxed but they are awake. Then the beta represents a state where someone is actively thinking. Yeah, and this can also be a state where someone is in a problem-solving state. Then we also have gamma, which is a high cognitive functioning state. Yeah, then we're going to proceed to this part that is going to help to this function that is going to compute band power for a given band. As you can see, here, this function defines compute band power data is, yeah, like this is going to help us process each EEG file. So it applies the filter to the EEG data. So like you can see the ranges and a better bandpass filter, data, low cut, high cut. Yeah. So then the next step is to process the EEG file, whereby it reads the EEG data from each EDF file using that MNE. library that we imported. Then after that it extracts data values, sampling frequency and channel names, sampling frequency and channel names. So this filter, it is applied, this filtered data, it applies the bandpass filter in that range to get general EEG data, like this line. Then here it gets the data sampling frequency, and yeah. So I'm going to invite my colleague to take you through the remaining parts. Thank you.
Good evening. So I'm going to start from where my colleague stopped. And my name is Kahunde Oji. Yes. And my student number is 23007086649. So I'm going to take you through the rest of the code. And I'm going to start from here, line 58. So basically what this part of the code does from line 58 to 60, it plots the first 5 channels of raw EEG data. As you can see, it plots, here we plot the title, the X label, which is the time samples, and the Y label, which is the amplitude, which is also measured in microvolts. Then we proceed to the next, which is the PSD, the power spectral density. So what the power spectral density does, it basically determines it helps us to determine the strength of the different frequencies of the EEG signals. Yeah, it displays the distribution of power, the strength of the different frequencies in the EEG signals. Then that's from line 69 to line 75. So when we proceed to the hist plot, this is basically a histogram. And what the histogram does is to show how many times a frequency is appearing. For example, is it low, like how many times a frequency is appearing? It displays the distribution of a single variable by dividing the data. Yeah, so here it helps us to determine if the frequencies are low or moderate or high. It basically shows the number of times a frequency appears. Then for the box plot, this one is used to determine outliers. These are very extreme signals, those that are out of range. I would also call it noise. Yeah. So that's what the box plot does. And here in the box plot, so our box plot helps us to determine the outliers and the skewness. Yeah. And here, okay, basically what the box plot, the hist plot, and the PSD, these three things help us to determine the distribution of our data. Yeah, it helps us to understand the patterns in the data. And then we go to our different variables here where we have the mean value. The mean value helps us to determine the average of the frequencies. Then the standard value helps us to determine the rate at which the frequencies are fluctuating, how they keep changing. The minimum value is a minimum frequency. The maximum value is a maximum frequency. Then the median value is that one that's in between the two, the minimum, the maximum. Then we have the skewness value and the kurtosis. This basically help us to determine the shape of the graph. Then we move on to the data frame. Now in the data frame helps us to, sorry. So the data frame helps us to organize and manage our data, the different data we have. in these different variables, we can see they appear here again, the mean, the standard deviation, the maximum, the minimum, the median, the RMS, skewness, and kurtosis. Yeah, so here, it basically, in the output, it will print out the statistical features, which are these ones. Then we proceed to band powers. This shows the power of the different frequencies in the bands. And like we talked about them before, the bands are the different frequencies that we're using to determine brain activity, which is the delta waves, the theta waves, the alpha waves, beta waves, and gamma waves. So this basically determines the power of those frequencies, this code here. Yes, then it will print out like the brain activity in the frequency bands. Yeah, the frequency bands, like I said before, are those different frequencies. The title, the label, the X label, the Y label. Yes, then the correlation matrix basically shows the different responses of the signals all together, like how they are relating, and it will output something. So in the user output, this is basically a navigation through, it helps us to navigate since our data set contains many folders in one folder, and those folders all contain different files. So it helps us to navigate through the files. So I'm going to briefly take you through a demonstration of the output. Yeah. So when I run this code, it's going to output a graph for me of raw EEG data. Yeah, so here we are seeing these different signals. Basically, this graph has no brain activity in it, and it shows the counter and the timestamps mainly. Yeah. So we have the red lines, as you can see, and the purple lines. So in this case, we don't have any brain activity, like I had mentioned before, but we have the title, which is raw EEG signals. And then on the y-axis, we have the amplitude, which is measured in microvolts. And then we have the time samples, the time at which the EEG signals are measured. So we have these, when you look at these lines, these ones that are going out of line, we also refer to them as outliers. Now, these are the extreme signals. As you can see, they are way out of range. Then we go to these next ones. You can see the purple and the red. So basically, this graph does not have any brain activity, like I had said before, but if there was brain activity, we would see a blue line or a green line somewhere. But in this file, we do not have any brain activity. That's it for the code. Thank you for listening to me, and have a nice day.